Our next speaker is Nathan Clark from Ganymede. He's the CEO and founder who's going to talk to us about implementation patterns for ASM. So Nathan.
All right, thank you. All right, yeah, so looking forward to the presentation today. I'm Nathan. I'm one of Ganymede's co-founders. I primarily focus on our commercial and solutions side at Ganymede, and in general come from a background in data infrastructure and machine learning. For those of you who don't know about Ganymede, to give a quick overview of what we do. So we are a data connectivity and infrastructure platform for the life sciences. We focus on providing modular infrastructure tools and a developer platform built on top of that for a lot of use cases around connecting lab instruments, connecting ELN LIMS systems, connecting applications and databases in life sciences, and essentially building the data flow that I think a lot of people here have probably seen that they have to build themselves, building out pipelines and AWS and storage and versioning and traceability. Our goal is to be the universal infrastructure of that data flow. And to talk a little bit more about what we do at that level, so we break down the components of our stack and how we try to get data from point A to point B into these different layers. We provide agents and connectors. So we provide these different chunks of capabilities to provide the infrastructure that we oftentimes see people having to build. So one big piece of it is agents and connectors. We have a framework for installing programs on Windows machines that can be configured to do everything from capturing files to communicating with APIs, OPC, COM objects, et cetera, whatever is needed to get the data off the instrument into the cloud, where we can provide an SDMS layer, traceability model built on top of all of this. And then it goes into what we call lab as code, which is our pipeline framework for doing computing and analysis on this. Because as you go from left to right on this chart, our goal is to say, we want to get all the data and have it all and be in a fair format and be archived and saved for you, but then also further get it all the way into its end destination. We're very, very, very focused on business automation for the scientists with their hands. We want to automate the data entry into the ELN or LIMS system because that is a further gold standard to get to that provides both good benefits for the scientists and gets an even richer data set oftentimes in terms of contextualizing it. So our lab as code system, which I'll talk a little bit about, that's where we've implemented the ASM models and how we compute on this data to take raw data, automate the analysis if we can, break it down into some output statistic or result that actually is going to go into the ELN or LIMS system and then inject it in, or we can create reports or whatever is needed. And then all of this can go into client data infrastructure. So that's a little bit about our platform. I'm going to get a little bit deep on the infrastructure side here in terms of going through, or in terms of the data side, in terms of talking about how the system works and how some of this traceability works and where Allotrope plays into that. Because this is the fun stuff for me, having a background in data infrastructure. I like to nerd out a little bit on the database side, and this is a great place to do it. So going from left to right here, this is our model of how we've implemented ASM and how data flows through Ganymede in general. We'll get some data from the instrument, like an API result or a file or something like that, and then we'll parse it out. And then that parsing is just at a protocol level. I want it to be in a pandas data frame. In Ganymede, we use pandas data frames as sort of a generic interface because once the data is in that format, it can be remapped, but that mapping is just from data frame to data frame. Everything, to the extent that we can get it, is a data frame interface, which helps facilitate analysis. So files go into that, but also ASM goes into that. As you go from left to right here, left to right is the data flow as you're converting things from files to parsed raw data to tabular data and then into that statistic. But then also we can compose in different schemas and mappings here. So ASM is also just a schema that's composed in. What we do is we unroll the ASM model into this tabular format. That tabular format is available in Ganymede's internal SDK. And then people can validate that schemas are actually conforming to that mapping. We have a validator system built in a layer called, a system called Pandera. And so in mapping data into the ASM model, you effectively say, is this data frame conformant, yes or no? If it's not, what's the difference? What do I need to map or remap to actually make sure that this data is in the right columns and types and so on to get it in there? And then that makes it easy for us to, from there, say, okay, well, we know this data is in ASM, so when we run some analysis on it and compute a statistic, we can assume the data format, and we can assume exactly how that data frame is structured. So that's quite nice, and we have adopted ASM as our, if people want to standardize their data at that structural semantic level, that is our default available in the system directly in the SDK. They're not required to do that, but we encourage it if possible. So one more word on who's actually doing this. Because we are a developer platform, many times it's our implementation folks who are going in and actually building out these code-based configurations for people, building the agents or deploying them. We have a pretty big library of agents and connectors for hundreds of instruments, but they're also very adaptable in code, so our implementation people will do that. But also we have clients that do it themselves. We have third-party consultancies that will get in there and be writing code. So the ecosystem of analysis and connectors and agent snippets that we've accumulated is quite large because we have a lot of people outside the company developing on this and therefore using ASM. Our data integration paradigm that we use for this is to separate things out into these three layers. So we separate out what we call network integration, the data capture. How do we get the data out of the on-prem system or out of whatever silo it's in into an accessible area in Ganymede or in the client's infrastructure? We can ride on top of S3 buckets or Azure storage, et cetera. So how do we get that data out? Step two is the parsing, and that's where that parser and mapping into, if you are selecting something like Allotrope, the data integration layer. And then step three is the semantic integration, and that's what we mentioned about the business analysis side of a lot of this, where we want to ideally take that raw data, and if we can, immediately automate the analysis, automate what scientists are about to do with their hands on that data so that it can be calculated, put into the LNR limbs, and we have that much more of a rich data set of knowing how it was used throughout the process. And that goes in reverse, approximately, when you're writing data too. We want to use data frames as this universal interface. We want to have analysis and mappings that can assume some data structure. Could be full custom schemas, it could be something like ASM, and then use that to write data back too. One important piece of this, to go back to this diagram, is that we see the data flow as join conditions. So the title of this presentation was how to map anything into Allotrope. And the way that we help facilitate that is that we want to make sure that as data goes from left to right and it's parsed and analyzed, we can make sure that anything that's lost in the standardization process, of which there can be quite a bit, because the diversity of instruments is quite high. The data that comes out of them is oftentimes very different, even between the same two models of instruments. And sometimes that's for no good reason. Certainly, I think there's a lot of cases where there's just zero effort on standardization in a lot of lab instruments. But sometimes that's for good reason, because they have new features and they have certain capabilities. I can't count. We do a lot of work in flow cytometry. We have a lot of integrations with flow cytometers and FlowJo and systems like that. And I can't count the number of flow cytometers that have some cool bell or whistle on them that is actually quite valuable data and doesn't conform to any model. So our goal with this is to say, you can join backwards to the original raw data if you need. We'll parse and standardize what we can, because we see that mapping from the raw data into, in this case, ASM. We can see that mapping. So you can take the ASM data and say, this is my standardized data, but I also can have an easy, quick reference, literally in a SQL query, if you'd like, back to the original raw data to further join on some of that unique data or join on metadata. The paradigm is true between metadata and this kind of unique data. It's all about just having all of this in one data space that can be connected and joined together. So this is a literal example of constructing that query to join data across the ASM mapping that we do in Ganymede. And this is a pattern that we've established with our clients. With some clients, we've implemented it for them. Some clients use ASM themselves. In this case, what we're doing is we're saying, every row in Ganymede by default has a metadata ID. That's part of our traceability model, to be able to say, I know exactly, as things move from left to right, I can always trace back exactly what version of what code ran, what version of what data ran, so I can completely reconstruct this entire lineage. That's part of our purpose in creating this infrastructure that works out of the box for this kind of life sciences data connectivity and data flow, wet lab data flow stuff is this traceability. But I need to be able to join across it. So we have this row level metadata that says, for this data, what execution context actually wrote it? What node, what step in our lab as code pipeline actually executed with what code version? So I can join across it and say, I literally know this row of data was used to compute this row of data at the version level. And that allows you to actually join together additional data that's lost. So in this case, maybe you're only able to standardize columns B and C, and column A is some unique data that's not part of the standard model, but it's still there. I can still join on column A through this query if I'd like. And this is representative. It could be a whole schema. Usually it's actually a different table of data that's that unique data. So one model is to join it, as I just described, going through that metadata ID, we call the MID in Ganymede, where you're just saying, okay, I'm directly joining across that transformation from raw data to some standardized output. We also like to contextualize all of this against some sort of sample ID or batch ID or ELN ID, whatever we can get to give some context to the data and its metadata. In this case, I've just called it sample ID, SID. But this is where, because we are very focused on automatically writing data into the ELN or LIM system, that allows us to know through context or through maybe writing out the instrument file into the instrument, we have that sample ID in Ganymede and we can track it too. So tracking the sample ID through its lineage as it goes from step to step, from parsed data to analyzed data to final data that's going into an ELN or LIMS in Ganymede, that is another way to associate this data together. So I like the theme of loops that's emerging a little bit in some of these presentations, and our version of the loop, which I think is a very specific, like, instrument execution unit operation version of the loop of the data lifecycle with Ganymede, is this flow of running a lab instrument. This is the most complete integration. This is the gold standard that I think very few people are able to fully get to outside of lab automation context, but we're hoping to drive more and more with our clients, especially on analytical instruments, is to say, ideally, you define your instrument run or batch or whatever it is in your ELN, in your LIMS, in your MES. We do a lot of work in manufacturing as well. Whatever it is that's a system of record, you define your run there. We will actually take that out with the context, load a plate map or work list or a configuration file onto the instrument, and that's how we encode that sample ID or batch ID in. We, through our agents, will write that file in, instrument consumes it, runs it, and then whatever output has that will have that sample ID going through. So when we capture the data and then parse it into fair data, ideally in Allotrope, and then analyze it down and put it back, we already know where it needs to go, and we've established that sample lineage. So summarizing a few of these principles that we've learned over time through seeing how people build out their infrastructure and build out their wet lab connectivity. One is that we see joinability as the gold standard of data traceability. There's a little bit of a sense here of audit trails being too simple of a data structure that are helpful and are good for compliance, but don't really enable systematic traceability. You want to be able to actually join your data back in a query system to be able to say, if I have some data here in a system of record, I don't want to have to go through the audit log to find it. I want to actually have a query that can give me all the context, all the information, all the versions of the code that ran it or the systems that put it there. That is the gold standard in our minds. That requires that full circular life cycle. That requires a lot of infrastructure and connectivity. That is helped quite a lot by standardizing the data, standardizing the scientific data, and then also co-locating that structured scientific data with business schemas as well, if you can, in a single data layer. That also touches on the circular integration side. But I think a big thing in the circular integration side that we've seen on the second point here is that when clients choose not to necessarily adopt something like Allotrope or choose not to standardize their data, back to the comment from the Benchling presentation, they're doing a bunch of one-off analyses. They're not seeing necessarily the dividends in having the standardized data. They don't know naturally to have the standardized data in a standardized format. We really try in our system to make sure that we have lots of things that consume the standardized data. That's another reason that we do this full circular integration, is to try and have things that consume the standardized data, because that consumption, that pull model, rather than pushing from the instrument and saying, let's get all the instrument data standardized, having something that says, if you have data in this standard, you can automate your assays in this sense. You can automate this analysis. Here's this out-of-the-box package for some sort of scientific analysis that you need to do. That's tremendously helpful. So we tend to do that within our deployments and say, here's a whole bunch of analyses that you can use for your particular context. And that helps incentivize people to structure their data in more standard format. And then finally, really rigorously separating out these infrastructure layers from each other. We call these we would phrase it as making a thick semantic layer. You want to have all of your business logic in one place and have it all against a single type of interface. SQL tables, data frames in our case, or NoSQL tables, some sort of singular protocol that you can say all data transformations are against. That helps a lot, because you don't want that to bleed into your analysis. That instantly, if you have different formats of data in different systems, some of it's in JSON, some of it's in tables, some of it's in raw files, that just instantly breaks any sort of composability or relatability that you have between your analysis code across different locations. And so our hope with this is that our impact that we can drive here is a lower barrier to allotrope adoption through a couple ways. One is through this infrastructure being ready to go out of the box for clients. We have everything from very unique infrastructure tools. We have a system called virtualization, for instance, that can run entire Windows applications in it to either automate or give users a way to interact with Windows applications like Flojo, for instance, in a way that's traced into the pipelines. We oftentimes will deploy more cutting edge stuff like that for some of our enterprise clients, and we work with a number of folks in the enterprise space, 4 of the top 20 large pharmas. But also for our smaller clients who don't even, they can't even dream necessarily of setting up a traceable pipeline. We have dozens of cases where we are their first data infrastructure, or where they have S3 buckets set up in AWS and that's about it. And then we can layer on top and say, here's something that's ready to go, both the infrastructure, but also the traceability model, and also ready access to standardized data models. So hopefully they can adopt this better from the get-go. Our hope then also is that by providing a single development plane over all of this, you write code into Ganymede. Ganymede is a developer platform, and whether you're doing that as a client or our implementation services are doing that, this can be an environment that, through having the allotrope models and other data standards natively present as in our SDK from the get-go, people can get used to from day one referencing those. People can just start writing code that says, I want to point at that lab instrument and say, I know the data is ready to go because it's a data frame in Ganymede now because it's connected. Now I can write my mapping over to something like ASM. So that's our presentation, and we're having a lot of fun with this on our technology side. So hopefully helpful.